Hello, my name's Adam Lefaivre. I'm a researcher from the University of Lethbridge, and I'm one of the authors of the paper, A Novel Genre-Specific Feature Reduction Technique Through Association Analysis. And the other author is my supervisor, Dr. Zhang, also from the University of Lethbridge. So large volumes of music have been digitized, and they can be found through streaming services like Spotify, for example. Maintaining all this music by hand is basically impossible. So there's music information retrieval, which seeks to handle tasks like genre classification or playlist recommendation. Classification often uses features, and genre classification can use acoustic features, and if there's too many, it could cause problems with the classification, reducing the classification accuracy, or just have too much computational complexity. So reducing the number of features is generally a good idea. So the main problem that we're trying to solve is to remove redundant features through association analysis. So the first step is we characterize each genre using a list of feature value pairs, which we also call feature value sets, FV sets, using association analysis. Now the main algorithm in association analysis is the a priori algorithm, which you can think in terms of the market basket analogy, where a certain percentage of customers in a supermarket buy certain items together. And this gives you a feature value set, what we're calling a feature value set. Then in the second step, we examine feature value sets across genres through different strategies, and we have a couple strategies that we propose, and we remove redundant features. So we have three algorithms that are going to be discussed here. This first algorithm basically sets up the feature reduction algorithm that's next. So you can imagine we have a data set of feature vectors with labels, and we balance each genre to have the same number of songs. That data set is composed of real values, so we bin that to have discrete values, and we use the equal frequency binning method because in previous research we have seen that this binning method outperforms other binning methods. Then we split it back into genres, and we split it into training and testing data. Now the training data goes through this process where we call a priori, and we collect feature value sets, and we append them to a characteristic list for each of the genres. So this happens then a certain m number of times on that training data. So now we've come to the feature reduction method that we're proposing in this paper. So we can imagine from the previous algorithm, we go through these M training steps, and now we have characteristic lists for each genre. And the actual algorithm itself is quite simple. So we're going to look at each feature, and we're going to see how many times it occurs in a characteristic list, and then we're going to see how many times it occurs in all of the characteristic lists of each and every genre. And if that is less than some delta value, well, then we can either, one, we can remove it from all of the genres, or the user can choose to remove it from that specific genre. So when it gets removed, it's actually removed from a feature value set. The whole feature value set gets removed for that characteristic list. So now a higher delta value means that it's less of a strict removal threshold, and a lower delta value means it's more of a strict removal threshold. So now we're going to discuss this last algorithm here, and after we perform the feature reduction, we have these cleaned up characteristic lists for each genre. Then we go through this pairwise comparison, which generates these accept differences. So we have a sort of a fuzzy check. So if one feature value set has two features in common with the other feature value set, then we remove it from that one genre. So we go through and we do that for each pair. And we end up with these even more cleaned up characteristic lists. And so previously we have seen that a more strict threshold there actually supplies a better classification accuracy. Now after that we have a testing piece come in, and we count the number of matches, or the number of times that any given feature value set is a subset in that piece for each of the differences that we calculate. And if, say, for this pair, say it's the first genre gets more counts than the second genre, and this one, that same genre gets more counts than this other genre, well, then that genre gets 2 points for that testing piece, and so we consider that testing piece to be that genre. So we use two music data sets. We use the GTZAN data set and the Latin music database. The GTZAN data set has 100 music pieces per genre, 10 genres, and 76 features that are extracted using J-Audio. The Latin music database has 3,000 music pieces per genre, 10 genres, and 30 features, and this is publicly available. And we used lower minimum supports for the a priori algorithm in both experiments, and this is because more feature value sets can be generated and more information about the genres can be appended to the characteristic lists. So we stuck with lower minimum supports here. So I've already briefly discussed the findings in previous work that we've done having to do with lower minimum support, equal frequency binning, and the strictness of the pairwise comparison threshold. But what we found in this work was that features removed at a less strict threshold are also removed at a stricter threshold. So that is to say, we continue to remove the same feature if it surpasses a less strict threshold. So when removing initial portions of the overall feature set, we are also removing more correlated features, and the way we calculated that was we looked at the average Pearson correlation of the features that were removed against the average Pearson correlation in general across all the features, and if that value is greater than 1, then we know we're removing more correlated features on average. So we can achieve similar, if not better results, depending on the data set and the features used after feature reduction. So I apologize in advance because I live next to a busy road, and if there's car sounds and big trucks driving by, it could get pretty noisy. So let's talk about some experiment results here. So we have a delta threshold, and if that is surpassed, then all of the genres have that feature removed, and any feature value sets with that feature in it removed as well. So we're going to talk about the GTZAN and the Latin music dataset here, and the key takeaways are just that the correlation analysis stays above 1, generally, except for in this experiment, but generally they do. And the other key takeaway here is that we're able to surpass the in the GTZAN experiment, we're able to surpass the accuracy if there was no features removed. So 64.5%, we remove 3 features and we get 64.6%. It's not much of an improvement, but it's still an improvement, and we're still able, for example, in the Latin music dataset experiments, we're still able to use a high minimum support, which means less featured values produced, which means less computational complexity. And on top of that, we remove 11 of the features, and there's already only 30 features there. So we remove 11 of them, and we get 61.4%, which is lower than 71.8%, but it's still in the same ballpark. And of course, we see the correlation analysis here as well. So now we're going to talk about the results for this delta threshold option, which is to remove the feature and any subsequent related feature value sets that feature is in from just the one characteristic list where that delta threshold was surpassed. So the key takeaways are the correlation analysis is still above 1 most of the time. And so in the previous slide, without any features removed, we were able to get 64.5% for GT-ZAM. But here, we're able to get 65.6% average accuracy across the genres. And we're removing a maximum of 29 of the features, 29 of the 30 features, of the 76 features in total for GT-ZAM. And there's an average number of 9.2 features being removed per genre. So the same trends are occurring in the Latin music dataset experiment. So we have this correlation analysis here that's above 1 the majority of the time. And we're still able to have a high minimum support and remove a bunch of features and still come up with a classification accuracy across all the genres that's comparable to the original one, even though there's a whole bunch of features removed. So in conclusion, the performance is quite good, but in the future we're going to try out a few more removal strategies and extend the problem to multi-label genre classification, which is quite easy because we have the characteristic lists already set up. And we're also going to try it on more data sets. So we can further apply this to mood classification, instrument recognition, verifying tag annotations, playlist recommendation, as long as we have those characteristic sets per genre. So quickly, some selected previous works. Anything with Zhang, here, and here, is previous research in the same vein using association analysis. So thank you so much, and hopefully there's some discussions, and if there's any questions, I'd be happy to answer them.